Today we will discuss about concurrency control in distributed databases. So what do you mean by concurrency control in traditional databases? So as you know, when a number of transactions requires the same data item yet at the same time, that means more than one transaction like T1 and T2 is trying to access the same item at the same time. In a traditional database I am saying, but it cannot be permitted because this is a single data item that can be given to only one transaction at a time. Only after the completion of that transaction, then only this item will become free and some other transaction can access the same item. So this is the case of traditional databases. We have seen several concurrency control. So this is actually called as concurrent access to the item X. So this concurrent access to the data item must be controlled in traditional databases and also in the case of distributed databases also. So what we need to do with this distributed databases is to modify the concurrency control that is used in traditional database into a different protocol that uses in a distributed environment. Now when we do this concurrency control in distributed databases, so as you know, you'll be remembering some terms like locking protocols. We need to lock the item if one transaction is using that item, and after the completion of that usage the item must be unlocked. That is actually happening during the concurrency control operation. So the same mechanism is to be maintained in the distributed environment also, but the difficulty is several sites are participating in the transaction processing, and also there is a situation where the same data item is being repeated or replicated in several number of sites. So in order to overcome all these situations, we need to utilize special categories of concurrency control protocols in distributed databases. So when we use these protocols, we are assuming that each site participates in the execution of a commit protocol to ensure the global transaction atomicity. So atomicity is the major property of any transaction operation. So similarly in the case of distributed database also, we have to maintain atomicity. That means a single transaction, if it begin transaction, let it continue execute the transaction and commit or abort the transaction in a single sequence without having any intermediate stop and continue from that particular point. So in this situation, the assumption is here that all the sites that are participating in the transaction need to use a commit protocol that we were discussing in our previous examples. So somehow they have to stop the process by using a two-phase commit protocol or by using a three-phase commit protocol. So that is the first assumption. We are using any of these protocols. That is the first one. And second one is we assume that all replicas of any item are updated. So if a single item that is replicated in several sites, so if H is being replicated in several sites, after the completion of transaction, if there is any changes applied to the same item H, so initially if it was 3 and after the transaction if it was modified to 5, the same updation must be given to all other site also. That provision must also be there when we are applying a distributed transaction in a distributed environment. So we are taking two assumptions. First one is we need every site must be participating in a commit protocol, and second thing is the replicas where the same data item is being replicated is to be updated as and when the transaction finishes. Now for this concurrency control processing of distributed databases, we are using different locking protocols. So we'll be discussing on the various locking protocols applied in distributed architecture. The first one is single lock manager approach. This is the basic concurrency control locking based protocol, that is single lock manager approach. So as the name indicates, a single site will be acting as a lock manager. So assume that some 10 sites are participating in the transaction processing, but only one site will be acting as a lock manager. That means that single site will be managing all the request and allocation of lock for any data item that are participating in the transaction processing. So we'll be choosing a single site, for example SI, that will be selected as a site where the entire lock will be managed. That will be called as that single lock manager. So when a transaction needs to lock a data item, normally if any transaction may be initiated from any site, but it will be sending a lock request to only one site, that is SI, that was chosen as the single lock manager, and that lock manager will determine whether the lock can be granted immediately. So that single site will be maintaining all the updated information whether that item is currently being utilized by any transaction or whether that item is free now. So that decision can be easily made by that single site. So all the data item, for all the lock request, the request will be sent to a single lock manager system. Now if the item is available, if it is yes, the lock manager sends a message to the site where the transaction was initiated. So that item can, that lock will be granted and the site can access the data for its transaction processing. Now similarly, if the data lock cannot be granted, if it is a no, the request is delayed until it can be granted, and the message will be sent to the initiating site. That means the site which is given a request for lock request need to wait until that item become free, as some other site or some other transaction is currently using that particular item which was currently being requested. So that is the major operation that happens with a single lock manager approach. So among all the sites, a single site will be chosen as the lock manager, and all the lock requests for any data item will be sending towards that single site, and that site will be deciding whether the lock request can be granted, and if it is a grant or deny, that will be intimated to the site from where the transaction was initiated. Now the transaction can read the data item from any one of the site at which the replica of the data item resides. So after granting that lock request, maybe the same data item is present in many number of sites. So if the request is being granted, the transaction can access the same item from any site where that replica is available. It is not mandatory to access the same item from that single lock manager site itself. After getting the grant or grant to the lock request, the transaction can access that item from any of the site where the replica of the same item is present. Similarly, so reading can be done from any of the replicas, but whenever we are writing or doing some updation on that item, the write must be performed on all the replicas, because we should have the consistent data present in all the sites. So if H is being modified, when we are writing H into or after the completion of transaction, while writing H, we need to write that the changed item into all the replicas of that item that is present in different sites. So these condition also to be satisfied when we are using a single lock manager approach. Now let us see the advantages and disadvantages of single lock manager approach. The two advantages are, the implementation is very simple, because we are not bothering about all the sites. We are assuming only or assigning only one site for all the log related activities. So the implementation of that algorithm, that method is easier because we are not approaching any other site for granting the request or denying the request for a particular data item. So it can be done on a single site itself. So the implementation is simple. And the second thing is, if there is any deadlock, and deadlock handling is simple in the case of single log manager approach, because the deadlock can be identified by referring to that single system. If S1 is the site where all the log requests are being sent, by looking at that single site itself, we can identify the deadlock if there is any deadlock situation occurs, because all the data item, for all the data item, the log request and log grant, all the details are present in the same site. So for deadlock handling, we need to refer only that single site S1, whether there is any normal log grant is available or whether there is any deadlock is present in on any particular data item. So these are the advantages of single log manager approach. Similarly, there are two disadvantages also. First one is the bottleneck. So as you know, all the requests are sent to a single site S1, single site. So bottleneck means if more log requests are generated at the same time, the site will be in a busy mode because more requests cannot be handled at the same time. So that is a bottleneck for a single site that uses the single log manager or that particular operation. And the second disadvantage is the vulnerability because of the failure of that particular site. If that single site fails, the entire log management operation will be under failure. So no transaction that are initiated from any of the sites will be granted the data item or the log request. So the entire transaction will be under failure. So this is the basic logging protocol that is used with distributed databases, which is called as single log manager approach. Now the second logging protocol is called as distributed log manager. So in order to avoid the drawback of that single site failure, the distributed log manager, now the log manager ownership is distributed. That is the main thing on the second logging protocol. The log manager provision is distributed. That means different sites will be acting as log manager. Okay, so the functionality of logging is implemented by log managers at each site. So every site, for example, S1, S2, S3, etc., etc. So S1 will be acting as of the log manager for the items present in S1. Now S2 will be acting as the log manager for the items present in S2. Similarly, S3 will be acting as the log manager for the items present in S3. That means several sites are acting as log manager. So the log manager provision, that responsibility is being shared among different sites, and the items present in each of the sites will be the request for log will be granted based on the log manager present in those sites. Now the log managers control access to local data items. So if any items to be accessed from S1, the log manager present in S1 will be controlled. But when we are having replicas present, we need to use special protocols that we will be discussing later. So if HC is present only in only S1, we can manage its log request and deny on referring to S1 alone. But if HC is replicated, we cannot use this protocol. We have to use the variation of the same distributed log manager. So if same item is replicated, we need to consider that factor. But initially, basic distributed log manager deals with the data item. We are assuming that the item is present in only one site. and that site will be acting as the lock manager for that particular item. And every request, if S2 is requesting for X, the lock request for that item will be sent to S1. S1 will grant or deny that lock request, and accordingly the transaction will be continued. Now the major advantage of this distributed lock manager is as the work is distributed, we can avoid that bottleneck which was referred in the previous single lock manager approach, and it can be made robust to failures, because if one site failed, then also it will affect only those items which are present in that particular site. Any transaction that are using some other items from other sites can be executed smoothly even after the failure of one or two sites present in the distributed environment. So that is the major advantage of distributed lock manager. But the disadvantage of using distributed lock manager is the deadlock detection, which was mentioning in the previous case, is more complicated, because the deadlock is actually dealing with different data items and different sites. So in order to identify a particular deadlock, we need to refer more than one sites. We need to refer all those sites that are participating in the various transactions. We cannot identify deadlock or handle deadlock based on a single site as in the previous case. There all the informations were gathered in a single site, but in the case of distributed lock manager, the lock details are available in different sites. So just for example, for maintaining or making a deadlock cycle, we need to refer more than one sites. So it is a difficult or complicated task in the case of a distributed lock manager. Now we will discuss about various approaches that are part of distributed lock manager itself, but they will be managing the data items with replicas. So the special protocols that are used for handling replicas in the case of distributed lock manager, we will discuss one by one. There are mainly four categories. One is primary copy approach, second one is majority protocol approach, third one is biased protocol approach, and fourth one is quorum consensus approach. We will see one by one. So the first special case of distributed lock manager is primary copy. So the situation is we are having replicas of the same data item present in the distributed architecture. So the same item, for example, H is replicated on several sites. So which site will be acting as the lock manager? That is our question. So what we are doing with primary copy is we will choose any one of the replica of that data item, and that site will be, or that item will be considered as the primary copy. So for example, H is present in several sites. H is present in S1, S2 and S3. So randomly or by using any method, I will be choosing this H as the primary copy, and that site which contains that replica, that site will be, this site S2 will be considered as the primary site. So any one site with the same data item is considered as the primary copy. So there are several copies of H available. From that, one will be selected as the primary copy, and the site where that copy is present, that site can be called as primary site. So similarly, different data items can have different primary sites. So for example, this site S3 will be the primary site for item Y. S1 will be the primary site for the item Z. So different sites will be having different primary copies of different items. Now when a transaction needs to lock a data item Q, for example, it requests a lock at the primary site of Q. So it will give the any site, from any site, the request for lock will be sent to the site where the primary copy of that particular item resides, or it will send the request to the primary site of Q. So after that, it will implicitly get logs on all replicas of the same data item. So after granting that lock, it will get the lock on all the replicas present in all the sites. So for every item, it will send the lock request to the corresponding primary site, and after getting the grant on that particular lock, all the replicas will be getting the information. That means the information will be sent to all the replicas that the lock is being granted. Now the benefit or advantage of using this primary copy is, now the concurrency control for a replicated data can be handled similar to the unreplicated data. The implementation seems to be very simple, because when we consider for a particular item, the implementation is simple, because some items, some site will be considered as the primary copy. For some other items, some other site will be considered as the primary site. Similarly, when we consider from single data items, the implementation is easier, because for different items we will be having different primary sites. Now the problem or the disadvantage of using primary copy method is that if the primary site fails, for example, the item H or the item S2 was considered as primary site here. If that site fails, the transaction cannot access the item H even if the H is present in some other site also. That is the problem with primary copy. For example, Q is inaccessible even though other sites containing a replica of the same data item Q, because the request will be sent to only primary site. Primary site will be granting the request. If that site fails, even if the data is available in some other site, the request cannot be granted. So that is the drawback of using primary copy method. Now the second category, that is called as majority protocol. That is a variation of the first one. So distributed lock manager, the second protocol that we are using is majority protocol. Now the local lock manager at each site administers lock and unlock requests for data items stored at that site. That was the procedure followed in our previous case. Here also, the local lock manager at each site administers lock and unlock requests for data items stored at that particular site. So in the previous case, for different items, different sites was considered as primary site. But here, each site administers lock and unlock requests for all the data items present in that particular site. So there is a slight difference. Try to understand. Previous case, for some items, some sites are considered as primary site. But here, all the items present in one particular site is controlled by that single site. So when a transaction wishes to lock an unreplicated data item residing at one site, a message is sent to that particular site and its lock manager. So when a transaction wishes to lock an unreplicated data item, so if this is the situation, if one site contains the item X that is to be locked, the request will be sent to that particular site and its lock manager, because S1 is having the lock manager for all the items present in S1. So X is also present there. So if somebody is requesting for X, the request will be sent to the lock manager of S1. If Q is locked, in the case of unreplicated, I am saying X is present in only X or Q, whatever it be, it is present in only one site. If queue is locked in an incompatible mode, then the request is delayed until it can be granted. That is a normal case. If queue is already being utilized by some other transaction, the requested transaction or site need to wait. When the lock request can be granted, the lock manager sends a message back to the initiator transaction that it is being granted. That is the normal case. So this is for unreplicated data. So for different data items, or for all the data items present in one particular site, that site will be acting as the lock manager. But now the request for each item will be sent to the site where that particular item resides. That is for the situation where we are having unreplicated data items are present. But in the case of replicated data, we need to use some other approach. So in the case of replicated data, if Q is replicated, for example, if Q, assume that this is Q and Q is replicated in S2 also. For example, it is replicated in S2 also. If it is replicated in n sites, then a lock request must send to more than half of the n sites in which Q is stored. So as the name indicates, majority protocols. So assume that Q is present in some 10 sites. For example, I am giving an assumption. Q is present in 10 different sites. Now what this majority protocol is doing is, the lock request is sent to more than half of the n sites. Means more than half, that is 10 by 2. 10 by 2, that is 5. More than half means 5 plus 1, that is 6. It will send a request to at least 6 number of sites where the replica of Q is residing. That is more than half of the 10 sites in which Q is residing. It is not required to send this request to all the 10 sites where the queue is residing. It is a mechanism where we are sending requests to more than half of the total number of sites where that particular item is present. Now after sending that request, the transaction does not operate on queue until it has obtained a lock on a majority of the replicas of queue. So the request sent to 6 number of sites. Now each site will be granting. So site 1 will be granting, site 2 will be granting till that transaction cannot be proceeded. Site 3 will be again granting. Site 4 is granting. Now 4 out of 6 more, that is when it gets majority of response, lock grant from different sites, we can continue with the operation on queue. If some sites are under failure, maybe we will not be getting majority of odds. It is just like getting odds. If a transaction is requesting for an item, it will send request to more than half of the site where that item is residing, and it is expecting some responses, that is lock grant. And if it is getting majority of grants, that means if request sent to 6 and if it is getting some 4 lock grants, it can access the item queue for that particular transaction operation. Now when we are writing or updating the data item, the transaction performs writes to all the replicas. So for reading, we need to access the lock grants from means whatever be the read or write, whatever be the transaction request, we need to get majority of lock grants from the total number of site to which we are sending a request. Then the process can be continued with that particular item if it is getting a majority of response. Then after the completion of that transaction, the write, when some data item, for example queue is being updated, the updation must be applied to all the replicas where that particular item is residing. It is not only for more than half, or 5 plus 1 6, or it is not only for 6 or 4. It must be applied to all the site where that particular item is residing. So that implementation must also be there with the majority protocol that uses replicated data. So unreplicated operation is similar to the normal case, but replicated data we need to use a special category majority. It is just like getting more odds or more log grant from more number of sites. That item can be utilized for the transaction operation. Now the advantage of using this majority protocol is it can be used even when some sites are unavailable. So in that for example, the request was sent to 6 sites, 2 sites are not available, but we are getting response from 4 sites. We don't bother about these 2 sites where the sites are under failure. We are getting majority of responses. So even after some sites are under failure, the transaction can be continued. That is the main advantage of using majority protocol. Now the drawback of this majority protocol is it requires more data transfer. That means more than half, n by 2 plus 1, to that is one-way request, that is for lock request, and response from each of those sites, that is log grant or reject request, will be sending back to the initiator. So 2 into n by 2 plus 1 messages must be sent between the transaction initiator site and to the different sites where that particular item is present. So for lock request, it must send 2 into n minus 2 plus 1 number of messages. So more than half we are sending request, and reply will be getting the responses. That is why 2 into n by 2 plus 1, and n by 2 plus 1 messages for handling unlock request. Unlock request, we are simply sending a request for unlock. Only one way the server will be unlocking that. It won't be sending a response back. That is why n by 2 plus 1 only required for an unlock request. So we need to have more data transfers between the different sites that are participating in the transaction operation. Now there is a second drawback, that is more chances of having a deadlock even with a single item. If you are having only one item that is being participated in the transaction, there is a chance of deadlock. So consider a situation where an item Q is being replicated in S1 to S4. It is replicated in 4 sites, S1, S2, S3 and S4, and the transactions present are T1 and T2. They require Q. Now further consider that T1 acquired the lock from S1 and S2. So T1 gets the response from S1 and S2, and at the same time T2 also receives from S3 and S4. Now both are having 2 grants, so there is no majority. So no transaction can currently access the item Q. That forms a deadlock. That means we cannot continue with the transaction. So even with a single data item, there is a chance of having a deadlock. That is the second drawback of using a majority protocol for distributed transaction concurrency control. Now third category to manage replicas in the case of concurrency control in distributed lock manager approach, that is called as biased protocol. Biased means we are considering some special or some priority is given for some special types of data access. That is why it is called as biased protocol. Now the local lock manager at each site, as in majority protocol, so it will be almost like majority protocol itself, as we were discussing in the previous algorithm. But this same situation, the request for shared logs are handled differently than the request for exclusive logs. So for different types of data log request, it will be handled differently. That's all. Previous case, it was a generalized case. For any type of log request, it will be following majority. If it is getting majority of response, it will be granting the log. But now there are two types of logs available, that is shared logs and exclusive logs. So what are these shared logs? Shared logs are normally read log. Read logs are normally called as shared log because read can be done by more than one transaction at the same time. And exclusive log means write log. Write is possible only by one transaction at a time. Read operation can be done simultaneously by more than one transaction. That is why the log read log can be shared. That is why it is called as shared log. But write log cannot be shared. That is why it is called as exclusive log. So about shared log, when a transaction needs to log data item Q, it simply requests a log on Q from the log manager at one site containing a replica of Q. So it will send a request to any one of the site where that particular item is residing. So there is no special consideration is given for read log. So any item, if it is being granted, any transaction can access that particular item. So a second transaction or a third transaction can also send a request for the shared log. But in the case of exclusive log, when a transaction needs to log data item in exclusive mode, it requests a log on Q from the log manager at all sites containing the replica of Q. So for read log, it will send request to any one site request is only required. But in the case of a write log or exclusive log, it need to send the request to all the sites that contains the replica of the required item. That is called as biased protocol. That means exclusive log or write operation or the item which is used for exclusive log will be given more priority than the read log or shared log. Biased. The advantages of using this biased protocol is it imposes less overhead on read operation. If we are accessing or if we want to have a read log to be granted, it is a simple task because a communication is to be made only to one site. Less overhead. But disadvantage is when we are writing, we need to have a request sent to all the sites where that particular item resides, and also the more response must be made from the different sites. So more data transfer and overhead due to these communication for the case of write operations. That is the drawback of biased protocol. Then we are using a fourth protocol which is called as Quorum consensus protocol. So it is the extension of biased protocol which was discussed in the previous slide, Quorum consensus protocol. So what do you mean by quorum? Quorum, when we are conducting a meeting, quorum must be maintained. What is the meaning of that? We should have more than half of persons for that meeting must be present. Quorum must be maintained, otherwise the meeting will be cancelled. We cannot conduct the meeting. So similarly, based on some quorum, we are deciding whether the log can be granted or not. So what is the speciality of this Quorum consensus protocol is, it is a generalization of both majority and biased protocol. So here we are considering getting majority of responses as well as we are giving some priority on read log and write log. Means biased means we are for read log we are giving less priority, and for write log we are giving more priority. So we are considering the majority protocol considered and the biased concept together in this Quorum consensus protocol. So it is a generalization for both these cases. It can be applied for these two cases. Now here in this quorum consensus protocol, we are assuming each site, or we are assigning each site a particular weight. For example, assume that we are having some sites like S1, S2, S3, etc. Each site will be given a weight. So now I will be giving a weight 1, for example. So weight will be given depending on certain factors like the importance of that site, the items, the importance of items present in that site. Anything can be chosen. Every site can be given a weight. Now we need to choose two values. One is read quorum, which can be represented as QR, and a write quorum, which can be represented as QW. We need to find out two values, QR and QW. Read quorum and write quorum. So how we are choosing these two values? So look at this condition. We need to find this value of read quorum and write quorum based on these two conditions. So these two conditions must be satisfied for finding the value of QR and QW. Now the condition is QR plus QW must be greater than S. What is this S? S is the total of all the site weights. Now here S1 plus S1 weight is 1, S2 1, S3 1. So total of weight is, that is S is equal to 3. S is the total of all site weights. Now S is 3, which we are considering in this particular example. Now we need to get QR plus QW must be greater than S. So we must choose QR and QW such that QR plus QW must be greater than S. So S is 3. Okay, so how we can choose QR? For example, I'll choose QR as I'll take one more site, S4 also. S4 is also having a site 1. Now here we'll consider S as 4. So in order to explain it easier, I am using 4 sites. Each site is having weight 1. So S is equal to 4. Now I will consider QR is equal to 2. One example, any value can be chosen. QR is equal to 2. QR is equal to 2 and QW is equal to 3. Now let us check whether these two conditions are satisfying. QR plus QW greater than S. 2 plus 3 5, which is greater than 4, which is true. 2 into QW, 2 into 3, that is 6, which is greater than 4, which is also true. Okay, so we can choose any values for QR and QW, but it must satisfy these two conditions, that is QR plus QW must be greater than S and 2 into QW must be greater than S. So what is the meaning of these two conditions? QR plus QW must be greater than S means any one of these value must be greater. That means read and write conflicts cannot be occurred. That is the meaning of this condition. That means we cannot have equal value for QR and QW. That's all. Sometimes more QR will be available, or sometimes more QW will be available. That means QR means more read request, QW means more write request. Any one must be more. So in order to avoid that conflict between these two, we are using QR plus QW must be greater than S. Why this condition is given 2 into QW, that or QW into QW? Why it is so? Because 2 write must not be in conflict. That means 2 writes cannot be done at the same time. Only one write can be performed at the same time. So in order to guarantee that, we are using the second condition, 2 into QW must also be greater than S. So only one write can be performed at the same time. So there will not be any conflict. Now the quorums can be chosen as is completed separately for, so this is actually for each item. So maybe this is for item H. For item H we are considering different quorums like 2 and 3, and all these sites are having the item X. Now for another item Y, we can use different uh, what do you say, site weight. Also we can use different read quorum as well as write quorum for another item. For each item it will be different. Now each read must lock enough replicas that the sum of the site weight that is greater than or equal to QR. So in order to lock replicas for a read operation, the total site weight must be greater than or equal to QR. That is the condition to be followed. If we are getting a total sum of site weight which is greater than QR, the quorum that we are getting, then all the read must be locked, or enough number of replicas must be locked for read operation. Similarly, for write lock, it must lock enough replicas with the sum of site weight, that is S, must be greater than or equal to QW. The meaning is, so this is QR, not Q1, QR. So if QR is 3, read quorum is 3, for example. So no, sorry, here it is in our example, if it is 2. If QR is 2, it must lock 2 or more number of what do you say, so S greater than equal to QR, right? So site weight is actually 4. So 2 or more, it must lock 2 or 3 or 4 number of replicas for accessing read lock. Now similarly, in the case of write lock, it must lock the condition based on the total site weight which is greater than equal to QW. So at least QW number of site must be locked or more than QW. Each write must lock enough replicas that the sum of the site weights that is greater than equal to QW. So minimum that much number of site with that item must be locked for the case of write lock also. So here it is the generalization of both majority and biased protocol, but we are considering an importance for write lock, as well as we are also getting odds, that is majority of lock response also. If some situation, if read is getting more responses, that situation read can be as required number of reads can be locked. But if you are getting more lock requests for write operation, we can have the lock grant for write operation. There it will be given a biased or importance for write lock also. So it is the combination of these two by using a quorum. If more quorums, if only 2 is for read operation and 3 is for write operation, so write will be given priority in this particular case. So some situation, the data item, the replicas may be overlap between these two transaction also, because so from these two maybe from these 3, one will be common for read as well as write also. Read and write on the same data item, that is also possible. But the transaction which gets maximum number of quorums will be given the lock grant, and it can continue with the transaction operation. So this is the major concept of quorum consensus protocol, where we are giving the two concepts of majority protocol and biased protocol. Now a second type of concurrency control mechanism that is used with distributed database system is time stamping. So the same concept is applied in the case of our traditional database system also. So what is this time stamping? So how we can control this concurrency? So time stamp based concurrency control protocols can be used in it can also be used in distributed system. Now every transaction, so how we will maintain this time stamping? Every transaction must be given a unique timestamp So every transaction on every site will be having its own unique timestamp. But while assigning this timestamp for each transaction is for example, T1 is given a timestamp. Similarly, T2 is given another timestamp. It may be present in some other site. So each transaction must be given a unique timestamp. So the transaction time will be different for each of these transactions. Now in this case, the problem is how to generate a timestamp in a distributed fashion, because the time concept, the timing of different sites will be different in different locations. So how we can have a timestamp that can be generated in a distributed fashion. Now what we are doing is every site generates a unique local timestamp using its logical counter or local clock by its own. The locking system, or sorry, the clocking system or the counter that is used in that particular site, it will be having a local timestamp and will generate a global unique timestamp by obtaining or concatenating the unique local timestamp which was generated in the site with the unique identifier of that particular site. So local unique timestamp, that is the timestamp generated by the local site, will be added with the site identifier, will form the global identifier. For example, site identifier is S1 and timestamp is like 950, or timestamp will be having all the extension of all the time details. So global unique identifier will be like S1 dot local timestamp like 9.50. like that we can have the global unique identifier. So global timestamp we are getting. Now how this concurrency can be controlled? By looking at the timestamp, whenever a request is sent on a particular timestamp where the transaction is expected to be executed or expected to access that particular item, that can be granted. If the variation in timestamp occurs, that entire transaction need to be aborted and need to start from the begin itself. So if every transaction is being provided with a timestamp for the access to different data items or for each of the operations present in the transaction, based on the timestamp, the items can be accessed without affecting one another. So this is the second type of concurrency control mechanism used with distributed databases. So but we are not giving more description on timestamp based concurrency control, but you have to be very careful about the different protocols used with this concurrency control in distributed databases. For these locking protocols, different types of locking protocols, variations of locking protocols, etc. So these portions are given importance in this particular subject, and you can mention some basics about timestamping for concurrency control in global transaction also. And finally, we are having one more point to be discussed in this particular module, that is three-tier client-server architecture. So this can be considered as a case study. So three-tier client-server architecture, which is very commonly used architecture nowadays for web-related applications. So if any program is related with web pages or web access, we need to use a middle tier also. So normally we are having two-tier architecture, that is a client and a server. But when a middle tier is being included in between, that can be called as three-tier client-server architecture, mainly and very commonly used nowadays for web applications, because most of the applications are now web based. So we need to use this three-tier architecture itself. So that intermediate layer can be called as an application server or a web server, which stands in between the client and server, the real server. Server means here in the database concept, server means the database system, the database disk where the data are present in the server. Now in order to access that data, we need to use some codings in the client side, and that is to be converted, or intermediate is standing in between the client and server database. So this application server is the intermediate, or web server. These two are the names given to that middle tier. Stores the web connectivity software and the business logic of the application to access the data from the database server. So for example, that middle server will be executing the ODBC or JDBC, like the logic for accessing the data from the server system. It acts like a field for sending partially processed data between the database server and the client. Now, three-tier architecture can enhance security. That means the database server only accessible via middle tier. So no client can directly access the database from the server system. It can be possible only through the middle tier. There will be a lot of comparison, security verification and all, or authentication. Then only they can access the data from the database server, and also the clients cannot directly access the database server. So this is the three-tier client server architecture. In the network terms, we can see the three layers: the presentation layer, business logic layer, and database service layer. So this is the internal database server part. This is the middle tier, where we are using business logic for the application, and presentation layer is the place where we are using our front-end forms. So this is the client, this is the middle server, or web server, or application server, and we are having the database server. So client will be writing a graphical user interface program or web interface program using HTML or any other tools, which will be forming the presentation or the front-end forms where the data to be collected or interaction to be done. And in the middle layer, we will be having the application programs or web pages, maybe by using JSP or etc. Several scripts are available for the middle layer communication to the server, which is the formation of business logic layer. And finally, we are having the database server, where we will be having the DBMS system, where we cannot directly communicate. Through the support of intermediate layer only, we can have the access to the DBMS, and that provides the security for the data that is present in the server side. So why we are describing this three-tier client server architecture in this situation is, in this module we are discussing about database system architectures. So this database system architectures normally provides the access to the data from the server with the support of a middle layer also. So we need to know the general three-tier client server architecture also. So that is why we are giving this simple description on three-tier client server architecture and its pictorial representation. So that's it for now. Now in this session we were discussing about the distributed concurrency control, various concurrency control protocols, locking and timestamp, and we have discussed more details about locking protocols, and also we have seen the basic three-tier architecture in a small manner. So that's it for the first module. First module is now almost over. The basic database system architectures, and in the next videos we will be discussing about the other advanced database concepts. Especially we will be focusing on object oriented databases in this particular subject. Thank you.